Okay, let's start. So the main topic for today is invariant bilinear forms. We said something about them last time, so let us recall what was that. So by definition, bilinear form B on G is called invariant if the following thing happens. B of commutator of x and z with y is the same as b of x with commutator of z and y. This is for every x, y, and z in G. And we also had this statement, and which is really very easy to see, that if I have an ideal, then orthogonal complement with respect to invariant bilinear form is also an ideal. And orthogonal complement is all x in G such that b of x with y is 0 for every y in I. So then this is an ideal. Also, we had a particular example, which is the most important example for us. It's a trace form. Right. So example. If I have a representation, V representation, or finite dimensional representation of G, then the following form, and we denote it as BV of x, y. And the representation also comes with homomorphism to GLV, right? So the form which is trace over V of rho of x, rho of y is invariant. And we checked it, and this is just really uses the cyclicity of the trace. All right. So that was what was the last time. So the first statement, the first new statement is the following theorem. So theorem goes like this. Let V be a representation of G such that BV is non-degenerate. Non-degenerate means that orthogonal complement to G is 0, right? Then G is reductive. Let's prove that. Okay, so to prove that, we will need the following. So suppose V is not irreducible. Suppose that there is some invariant subspace inside. Say W inside V is an invariant subspace. All right. Then I claim that BV of xy is sum of BW of xy and BU of xy, where U is the quotient of V by W. It's also a representation, right? So where U is V quotient by W. So why is that true? Well, let us just take some element x in G. Then I claim that in right, and let me now fix a basis like that. So I take some basis of W. So this is a basis of W, and then complete it to the basis of V. So Vk plus 1, V n. So B like this. So this is a basis. So in a basis like this. So this is a basis of V. Rho of x looks like this. So actually we have blocks, right? And since V is invariant, right, we will have a block here that corresponds to these first vectors, right? And then you will have 0 here and something in these 3 blocks. But what is this something? So actually here I will have, so this is row V, right? So the matrix corresponding to the representation V. Here I will have row W of x in the basis V1, Vk, right? here I will have something, I don't care what stays here. And here I will have row u of x. This is in the basis. So I will take an image of these vectors in the projection to. So I have a canonical projection from V to U, right? So I will have corresponding images of these vectors, which gives me a basis of U. So Vk. So let me just write it like this: pi of Vk plus 1, pi of Vk plus 2, and so on, where pi is a map, is a canonical projection from V to U, which is V by W. So this picture explains everything now, because we need to recall what is BW and BU, right, and BV. So this is a trace over a product of matrices, right? So I take one matrix of this form, another matrix of this form, multiply. So what stays, matrix that stays in these blocks, multiply matrix that stays in this block, multiply, and then I take trace, right? And this is a trace of this matrix plus trace of what's going on here, right? So therefore, so I explained why this is true. Right, so then trace over V of rho V x rho V y, right, is the same as trace over W of rho W of x, rho W of y, plus, because of these blocks, trace over U of rho U of x, rho U of y. So the claim follows. So we have this. This means that actually, so let me take V and write a composition series for it. So for any representation, finite dimensional representation, at least, we have the following. We have V, and then inside V. So we have like a chain of inclusions of representations, right? V1 inside V2, and then so on up to some Vm, and Vm is actually V. Such that Vi plus 1 quotient by Vi is irreducible. So this is called composition series, and we can find such thing for any representation V. So how to do that? You take some maximal sub-representation. This will be Vm minus 1. Then inside Vm minus 1, you'll have another maximal representation, and so on. And so that's how you do it. So consider composition series of V. Then, according to what we proved, so let me now apply this m times. Applying this m times, so maybe let me denote this as Wi, gives me the following. Bv of xy is b sum over I from 1 to m, bwi of xy. So I'm kind of boiling everything down to irreducible representations, because for irreducible representations, we know that commutant of G in radical G acts by 0. Right? So that's what we would like to use here as a next step.
Sorry, before we continue, I think I lost. What's the technique to prove this?
Yes. So I never finished, so maybe let me continue. So all the statements are clear so far, right? Right, so we're proving that if I have a non-degenerate representation such that the trace form is non-degenerate, then G is reductive. Reductive means, yes, the radical, so reductive is a reminder. Radical coincides with the center, or what is equivalent, commutant of G with radical is 0. So let me take x from the commutant of G with radical G. Right? Then this rho Wi of x is 0 for all I from 1 to n, right? Because Wi's are reducible, and we know that in reducible representations, this thing acts by 0, that we proved last time. So because Wi is Wi's is irreducible. But then Bwi of x and y is 0 for every y. Right? So I just take 0 matrix and some other matrix, multiply them, I will get 0 matrix. Of course, trace of 0 matrix is 0 for all y in G. Right? And this is for all I from 1 to m as well. So this means that now I'm using this. This means that V of x, y is 0 for every y and G. But we know that the form is non-degenerate, right, by conditions of theorem. So therefore, BV is non-degenerate. Therefore, x is 0. So this means that a commutant of G in radical G is 0, and we are done. So this actually means this is the same as this. So G is reductive. Okay, so any questions? So, Abner,
Yeah.
did you follow?
I was wondering why we can consider that the W of the beginning, that it's an invariant subspace. We always can consider that exists.
W's are not invariant subspaces, though. So we invariant subspaces are V's. So if they can, it might happen that there are no such V's. Then V itself is irreducible. So there's in this sum there's only one term which is By. It's Bv itself, right? But then the same argument works because V itself is irreducible, right? So take V. So if I take X from here, then rho V is 0 now, right? Because this in irreducible representation is X by 0. Then Bv is just directly equals 0 for Oi, Y, and G, just because rho V of X is 0. But again, since we assume that it's not degenerate X, this means that X should be 0, so therefore G is reductive. Okay. So the next thing, which is very important in the whole theory of Lie algebras, is the next object that we would like to introduce is called the Killing form. I think we already discussed it a little bit last semester. Did we? Maybe not, I don't remember.
No.
Ah, okay. So Killing form, definition. The form K of X, Y, which is B G of X, Y. So G here is a representation of G, like adjoint representation, right? So this is a trace of add X, add Y. Is called is called the Killing form. So what right, so this is the Killing form. In particular, you can construct what like elements of the center of universal enveloping algebra using the Killing form. That's why this could arise last semester. So for now, we will need the following two statements. So first statement is called, so maybe call them theorems. So theorem 1, or without numbering. So this theorem is called Cartan's criterion of solvability. And it goes like this. So G is solvable if and only if the Killing form of this, so the commutant of G with G, is 0. If the commutant of G lives in orthogonal complement, it lives in the kernel of the Killing form. This is one very important statement, and this is an instrument in structure theory of Lie algebras that you apply all the time. And another one, which is not less important, which is theorem called Cartan's criterion of semisimplicity. Cartan's criterion of semisimplicity. So it states that G is semisimple if and only if the Killing form is non-degenerate. Is non-degenerate. Okay, let me number them because it will be convenient for me. Okay, so let us prove them, since they are important for structure theory of Lie algebras. It would be unfair just to state them, I guess. So the theorem 1 follows from theorem 2 follows from theorem 1. So let us observe that first. Maybe let's formulate it as proposition. Theorem 1 implies theorem 2. Proof. So suppose that we proved theorem 1, and let us prove both directions of theorem 2. Right. So proof in this direction. Yes. So we would like to, so suppose that G is semisimple, and we would like to see that K is non-degenerate. Well, it's kind of natural what to do here. I take G orthogonal complement to G. This is called kernel of a form, right? So this is again all x in G such that K of x and y is 0 for every y in G. So we would like to see that this is 0, right? But G is semisimple, therefore we would like to prove that this is solvable, right? So goal to prove show that G orthogonal is solvable. Okay, so how do we do this? Yes, so of course we show that by by using theorem 1, because we kind of know the criterion for solvability. Right. So this is an ideal, and I would like to compute. I would like to argue that the Killing form of G orthogonal is 0. Then we are done, right? By the first theorem, because if it's 0 everywhere, then of course this thing is 0 as well, and so then G orthogonal is solvable, right? So our goal is to see that that K, so Killing form corresponding to particular, so we will have algebras and subalgebras, and we would like to distinguish between Killing forms of algebras and subalgebras. So I will use the upper subscript, so like that. So this is a Killing form of G orthogonal. So I claim that Killing form of G orthogonal equals just a restriction of Killing form on G, which is this K without superscript, to G orthogonal. So claim is K of x, y for every x and y in G orthogonal. So here, this is a claim that is true for every ideal. So if I have a Lie algebra, an ideal inside, then the Killing form of an ideal is a restriction of the Killing form of the bigger algebra. So why this happens? So we will just need to draw the same picture for the matrix of rho of x, so when we were proving this first theorem of today's lecture, and see that this is indeed true. So let me move to this board. So let me take x from G orthogonal, right? Then how does, so again, we will, we would like to see what is the matrix for rho, gx, right, in the following basis. So consider a basis of G, the following one, B, so you have first whatever k elements, they form a basis of G orthogonal, and then the rest is just a completion to the basis of G. Then in this basis, in the basis B, my rho G, right? So G is a representation of G as an adjoint of X. So let me. It's the following matrix. So remember, what's important here is that X is inside G orthogonal, and G orthogonal is an ideal, right? So I have, again, these blocks, right, corresponding to this partition of my basis. And I claim now that I have zeros in here. And in here, I will have row G orthogonal of X. And something in here that I don't care about. Why is that true? This is because G orthogonal is an ideal. If I take X and commute with something from not an ideal from here, this is why I'm explaining why here we have a 0. Then it jumps back to this ideal. Okay, so that's why you have 0 here. Right, so this is the only fact, we're using only the fact that G orthogonal is an ideal. So you don't have anything here. If it's a subalgebra, then we would have. But since an ideal, have like that. But once I draw this picture, everything is clear, right? Because you just need to remember what is K. It's a trace of a product of two such matrices, right? So I take one such matrix for X, multiply by another matrix of X. Again, I will have in both of them I will have zeros here. These two blocks multiply, and when I compute trace, there will be no nothing coming from this part. Only trace over this. But trace over this is exactly the killing form for G orthogonal, right? So this is exactly the difference between killing form on G orthogonal and killing form on K is that you taking the trace here over the smaller subspace. But this argument shows that a trace over the smaller subspace coincides with the trace over the whole subspace because you have zeros in here. So, okay, I don't think I will need to write anything more than I wrote here. So we have now this. But you see, for y and x from G orthogonal, just by definition of G orthogonal, k is just 0, right? Just here's the definition of G orthogonal, right? So if I take x from G orthogonal and any y, so it happens to be from G orthogonal as well, but it will be 0, right? So therefore, we have, so maybe let me not erase these two things. So therefore, kg orthogonal is 0 for every x and y from G orthogonal. And this means that, in particular, this means that by theorem 1, G orthogonal is solvable. By theorem 1, G orthogonal is solvable. And therefore, so G orthogonal solvable, since G is semisimple, then by definition of semisimple, it does not have any non-zero solvable ideals. In particular, this should be 0. Since G is semisimple, G orthogonal is equals 0, and we are done. Because this is exactly what it means for the form to be non-degenerate. So again, we proved this direction, right, using theorem 1. So if G is semisimple, then killing form is non-degenerate. Let's prove the other way. The other way is actually easier because So we assume that this thing is non-degenerate. The killing form is non-degenerate. So what you can say about G right away, according to the results of today's lecture? So what was our first theorem today? Yeah, G is reductive, right? So we found a representation such that the trace form is not degenerate. And this representation is adjoint, right? It means by the first theorem of today's lectures that G is reductive. Very well. So K xy is non-degenerate. Therefore, G is reductive. So I'm proving that G is semisimple, right? So that means that I'm proving that the radical of G is 0, right? But since it's reductive, it's the same as proving that center is 0, right? So the center of G is radical of G. So let me take something from the center. Then add x is just 0 matrix, right? Because this is a linear transformation of G such that I take a commutator, take a Lie bracket with x. Since x is in the center, it's just Lie bracket with everything is just 0. So this is just 0 matrix. Right. So therefore, K of x and y is 0 for every y, right? Well, because this is a trace, add x, add y. This is 0, so therefore. But by our assumption, this is non-degenerate. Again, then this means that x is 0. So therefore, center is 0, and therefore radical is 0. Therefore, G is semisimple. So we are done. Now let us see how to prove theorem 1. So I claim that theorem 1 follows from the following lemma. So this lemma is pure linear algebra, and so it's like some technical stuff. We will see how it's proved, but so let me have let H be a subalgebra in GL V. So be a subalgebra. So it's a matrix. So Lie subalgebra. So matrix Lie algebra. Such that well, I can take trace over V, right, of two elements of H So I would like it to be 0 if I take x from the commutant of h and h, and y just from h. Then, so these are conditions. Then y, then every x in h is nilpotent. So this is the lemma. But why theorem 1 follows from this lemma? So this is theorem 1. So we need to take h to be something. Well, we already, right. So theorem 1, right, so proof of the claim, right? So proof that theorem 1 follows from this lemma. And then for the rest of today's lecture, we would like to prove this. Maybe we'll skip something, but and we'll see. So proof of the claim. So which way I would like to do that? This way follows from the lemma, and the other direction follows just without lemma. So if I have this, right, let me take h to be the image of a joint representation image of G. Then, since we're proving this direction, so we assume this. Okay. Then, right. Then let us see that h satisfies conditions of the lemma. Right? So we would like to take any x from here, y from here, then the trace over the product should be 0. Right. So if I take x from h from the commutant, like the trace is linear, so I can assume that it's just not a linear combination of commutators, but commutator. Then x is at of some x prime, where x prime is in G, is in the commutant. This is because at is homomorphism of Lie algebras. Right? Because at is homomorphism of Lie algebras. Therefore, if I take some y from H and I compute trace of x, y, it will be trace over G, of course, of add x prime add some y prime, right? Since H is an image of G, then y is add y prime for some y prime in G. But this is killing form of x prime and y. This lives in G comma G, and this lives in G. Therefore, this is 0 by assumption. So we are proving this direction using lemma. So we assume that this is 0, right? So therefore, this thing is 0. Therefore, this trace is 0. So our H satisfies conditions of lemma. Therefore, every H from H is nilpotent. So therefore, every add x, right, where x in G is nilpotent. But this by Engel's theorem, like the second Engel's theorem, means that actually right, so this means that G is nilpotent. G is nilpotent if and only if right, so the lemma actually goes not like this. So every x is in H is nilpotent. So this is how lemma goes. Little correction. So therefore, everything in here is nilpotent, right? Therefore, add x as x from the commutant is nilpotent. Therefore, the commutant is nilpotent. And therefore, G is solvable. Phew. Okay, very, very well. So using lemma, we prove the theorem this direction. So maybe let's see the other direction, and then we will try to prove the lemma. So any questions about this? Because I'm going to erase that to prove the other direction. So the other direction. So we proved this. What about this one? Right. So I'm assuming that G is solvable. Then I have this. Right. Right. So in this direction, we should use Lee theorem. So by Lee's theorem, so since it's solvable, there exists a basis in G. So by Lee's theorem, there exists basis in G such that all rho v of G, of like this. So this is what I mean by at x, right, are upper triangular. But then add x for x from G, comma G is strictly upper triangular. Right, because this is a commutator of two upper triangular matrices. So therefore, it's strictly upper triangular. Therefore, if I compute, if I take x from G, comma G, and y from G, and compute killing form of xy, right? So this is a trace of something strictly upper triangular, x, add x, times something upper triangular. Something strictly upper triangular times something upper triangular will be strictly upper triangular. So we will have zeros on diagonals, and therefore trace will be 0. Okay, so we are done. Let us prove the lemma then. So the proof of lemma, so now I can erase all these criteria and prove the lemma, proof of the lemma. So proof of lemma uses some facts from linear algebra. So we will use the following facts from linear algebra. First one is pretty standard. I think you all know this. If you don't know, you can just read it in any standard book. It is Jordan decomposition. What is Jordan decomposition? If you have A, which is a linear operator on some actually complex linear vector space, then it can be uniquely decomposed. It can be uniquely written as a sum of semisimple operator and nilpotent. So this is called Jordan decomposition. So what is semisimple? For us, it just means diagonalizable. Okay, I mean the definition is that is actually closer to representation theory. Is that every invariant subspace has a complement which is also invariant subspace. But this is the same as being diagonalizable for matrices. And nilpotent, well, it's clear, right? So some power of this matrix is 0. Right, so this is semisimple, which is diagonalizable. And this is nilpotent. And moreover, both AS and AN, they are some polynomials of A. They commute, and they are some polynomials of A. And the second statement is the following. So we will need to define a new linear operator. So linear operator. AS conjugate. So this is just a notation. So how do I define it? So define as follows. So I take, so let lambda I and vi be eigenvectors and eigenvalues and eigenvectors of A, some spectral data of A. Eigenvalues and eigenvectors of A, right? That is, and moreover, they are eigenvalues and eigenvectors of AS as well, semisimple part. Semisimple part and A, they have the same eigenvalues. Right, you should think of, so you have Jordan normal form, right, where you have blocks, like upper triangular blocks, with eigenvalues on diagonal and ones on on the sub-diagonal, which is like one step over diagonal, right? So this ones on diagonal is, in a sense, an, right? And the diagonal with eigenvalues is as. So as and a, they have the same eigenvalues. So how do I define as bar? So I have a s vi is lambda I vi, but then I define as bar to have the same, to also to be diagonalizable, to have the same eigenvectors, but eigenvalues are complex conjugates. So there's no statement yet. We just defined some AS bar. But the statement is that add AS, which is a linear transformation of linear transformations, right? Just taking a commutator, right? So it's a linear transformation of GOV, right? Is some polynomial of add A such that P of 0 is 0. Sorry, it should be like that. So okay, this I will not comment. This one, it's more like a more special statement from linear algebra, right? So not like everybody heard that. So maybe we can discuss in so statement, is it clear? Yeah, this is the statement. Then this is a polynomial of add A, right? Where this polynomial has no constant term. All right, so this is justified by the following. First of all, add A. So this is also linear transformation. And it has its own semisimple part. Right? Every linear transformation has a Jordan decomposition. But this is, yes. And this is some polynomial of this. Right? Just because of Jordan decomposition, we know that semisimple part is a polynomial of original linear operator. All right. On the other hand, this thing is add AS. Well, just because, and nilpotent is the add of corresponding nilpotent part. Just because you can check that this is diagonalizable and add of AN is nilpotent. So the fact that this is diagonalizable, we can see right away. So if right, well, I just need this. I'm kind of justifying that why this is true, right? But at least we can see that this is diagonalizable, and we can actually see what are the eigenvalues of this. All right. So eigenvalues. So eigenvalues of AS are lambda i's. Right. But eigenvalues of eigenvalues of add AS then are lambda I minus lambda J for each pair I and J. This is because, like, if I have an eigenvector Vi for A and Vj, right, I can form Vi tensor Vj star. This is an element in well, if this is a linear operator on V, right? Then this is an element in end V, right? But then taking a commutator, right, is the same as acting on A on Vi. So as a the taking of commutator with A, with this element, right, is the same as acting by Leibniz rule on this thing. You act on Vi first by A, and then you act on Vj. But because it's star, you will have minus. So that's why commutator erases. And that's how you get lambda I minus lambda J. So lambda I corresponds to this term, and lambda J corresponds to this term. And so we're proving this, right? So we're kind of justifying this, right? So first of all, I have a polynomial Q, right, of add A, such that it gives me, if I plug in add A, I will get add AS. On the other hand, by Lagrange interpolation, I can do what? I can find another polynomial q prime. So by Lagrange interpolation, there exists polynomial q prime, which sends, so q prime sends lambda I minus lambda j to the conjugate of that. Well, it's just Lagrange interpolation. But these are eigenvalues of add AS bar, right? So lambda I, these are eigenvalues of add AS, then these are eigenvalues of add AS bar by the same reasoning. And so I claim then that P is Q composed with Q prime. So first I apply Q, get this, right? But from this to get this has the same eigenvectors and eigenvalues, right? To get from this add AS bar, I need to apply another polynomial, which is given by Lagrange interpolation. And so my P, this polynomial that sends that gives me add AS bar, is given by this composition. Okay, so this is some justification of, so Jordan decomposition, I assume everybody knows. This is some more special fact that we discussed. So now let us apply that. But this is what we would like to prove, right? Let me take X, right?
I'm sorry.
Yes.
In this trace expression, what is the product of?
Just product of matrices.
So they are an adjoint representation.
No. This is a subalgebra in GOV.
Okay.
So makes sense. I don't say, by the way, that this product is in H, right? Commutator is in H, right? But the product might not be. But the trace is 0. Yes, but this lemma you skipped all non-technical part. So this dilemma we needed to prove the Cartan's criterion, and it was applied to adjoint representation. Right, so now we're just using some linear algebra, like just doing some linear algebra. That's it. Right. So now let me take X from here, right? So proof of lemma again. So take X from this one, and then let me take X S bar, like I introduced before. Okay. So let me consider trace of X, X, S bar. So this is just sum. So let lambda I be, so lambda i's are eigenvalues of X. Then this trace is sum over squares of absolute values of lambda i's. So these two things, they are actually upper triangular in the same basis, right? But in this basis, this guy has eigenvalues lambda. This guy has eigenvalues lambda I bar. So this is sum of lambda I times lambda I bar, which is absolute value squared, right? But on the other hand, by conditions of lemma, this is 0. Not yet. Not yet. I just said myself that this guy is from G, right?
Again, repeat. What is x?
XS, so I take semisimple part of x. X is some matrix, right? This matrix is written as a diagonal matrix. Think of like diagonal and strictly upper triangular. I take diagonal. Then I conjugate all entries. Okay, so that's loosely speaking what's happening. So I have eigenvalues lambda here and eigenvalues lambda bar here, so I conjugate them. All right, so now I'm using that x is in the commutant, right? So therefore, it is y. Again, I can say that it's just a commutator because of linearity of the trace. So this is, on the other hand, trace of y z x s bar. Now I'm using invariance of this, right? So this is trace, but these two guys, they live in H. This is solid, right? Not in the whole GLV, but in H. This is some element in GLV. Now I'm using invariance. So it is trace of y and commutator of xs with z. And maybe I need to put minus sign here. This is an invariance of the trace form. But this is add xs applied to z. Okay, let me continue on this part. So add x, so this is negative. So we're trying to prove that this is 0. So then all eigenvalues will be 0 and x is nilpotent, right? So trace is trace of y and add xs bar applied to z. But this is the same as minus trace of y, and then I take my favorite polynomial p that I erased from here, right? This is as a linear transformation of h, actually of GLV, right? It's a polynomial of add x applied to z. And moreover, this polynomial doesn't have constant term in it. So it's just a bunch of commutators with x without z, without just z, all right? But this means, so this is, so now I can use, so this guy is from H, right? This guy is from H, right? And I apply a bunch of commutators and x is also an H. Right? So that's how we chose it. It's in the concomitant, but it's an H. So therefore, the whole thing is in the commutant. So therefore, its negative trace is just 0 by condition of lemma. Right? If I take something from H from the commutant, another thing from H itself, then it's 0. So therefore, we're done. So it means that lambda i's are 0 for each I. Right? It means that all eigenvalues of x are zeros. So simple part is 0. So the only what's left is an nilpotent part. So therefore, x is nilpotent. And that's it. So we proved everything.